Hello and welcome back. In this video, I want to talk about what happens if we try to apply Newton's laws in a reference frame that is moving. Now, the first thing I want to point out is that Newton's laws really only depend on the changes in the velocity, right? Newton's law says the sum of my forces is equal to mass times acceleration, but acceleration is change in velocity over change in time. So Newton's laws don't so much depend on my velocity as it depends on the change in my velocity. So in other words, if I'm moving, say, 2 meters per second and somebody applies a 10 Newton force on me, I'm going to accelerate at some rate. And if I were moving at, 100 meters per second, if that same force were applied, I would accelerate at the same rate. It doesn't matter that I'm moving faster. As long as the force is the same, my acceleration is the same. So that's what I've just said, is that Newton's law does not depend on velocity, it only depends on the changes in the velocity. Now what this means is that if I add or I subtract a velocity to every single particle in a system, then Newton's laws are still going to be the same, because my acceleration that I calculate is going to be exactly the same. Now why is this important, and what does it have to do with reference frames? Now, remember that we've talked about reference frames before. We came up with this formula VAB is equal to VAC plus VCB, right? This is the velocity of object A as seen by an observer B. This is the velocity A as seen by observer C. The velocity of object C is seen by B. Okay? So this is Galilean relativity. This is how we relate the velocity that we see in a moving reference frame. Now, why is this important? Well, if we consider acceleration, this is the change in velocity over change in time, so this is v final minus v initial over delta t. If I move at a constant rate, then when I calculate v final, right, so v final in a moving reference frame is going to be some v final, plus my velocity in my reference frame, right? So I don't know what we'll call this. We'll call this RF. This is the velocity of my reference frame. If I move at a constant velocity, then the velocity that I add or subtract to my final velocity is the same velocity that I add or subtract to my initial velocity. And so as a result, when I calculate my acceleration, this will cancel out, because I'm going to subtract these two velocities. So if I've added or subtracted the same number from my final velocity that I've added or subtracted to my initial velocity, when I take this difference, it cancels out, and I just get back v final minus v initial over delta t. Okay, so if I were calculating my acceleration in some reference frames, maybe I'll put a little prime here to denote that I'm in a moving reference frame. So these are my velocities in this moving reference frame, and this is how I calculate this. Notice I get back the same thing as I would get if I were in a reference frame that was still, right? That wasn't moving. This is very, very important because Newton's law only talks about changes in velocity. So what this means is that if I apply Newton's law in a reference frame that's moving at a constant velocity, then Newton's laws are going to apply. They're going to work, and we don't have to worry about anything. Okay? This type of reference frame, a reference frame that's moving at a constant velocity, so that means it's moving at a constant speed and in a constant direction, is called an inertial reference frame. Okay? So Newton's laws apply in an inertial reference frame. A non-inertial reference frame is any reference frame that is not moving with a constant velocity. So this means that it's either speeding up or slowing down, or it's changing direction. Newton's laws do not apply in a non-inertial reference frame. In fact, we can really easily see why this is. Okay? So for example, imagine I have a box, and this box is just sitting on the floor. Well, if we apply Newton's laws, this is really simple. This is like the first thing we talked about. We've got this force due to gravity, it's pointing down. I've got this normal force, it's pointing up. And my acceleration, in this case, is just 0. Okay, Now, imagine I look at this box, and I'm in a, let's say I'm in a car. So here I'm in this car. Okay, so here I am inside the car. If I look at this box in this moving car, okay, if the car is moving at a constant velocity, then what I see in my reference frame in this moving car is I see the box moving in the opposite direction with the same velocity that I'm moving in my reference frame. Okay? And so if I apply Newton's laws in this reference frame, well, I say, okay, well, this box, it's moving in this direction to the left at a constant velocity. That means that the acceleration of the box is 0, and that means that the net force acting on the box is 0. And in fact, if I go ahead and I apply Newton's laws, I see, yes, I've got a force due to gravity pointing down, I've got a normal force pointing up. The net force acting on this object is in fact 0. And that's exactly what I see. Is if I observe this box in a car that's moving at a constant speed in a straight line, I see that this box is not accelerating. I see that it's moving at a constant velocity in the opposite direction. Now, if my car were accelerating, okay, so if my car is accelerating to the right, and I look at this box, what I see from my reference frame is a box that is accelerating to the left. So if in my reference frame, actually I should say accelerating reference frame, so if in this accelerating reference frame, I look at this box, here's what I see. I see this box, and it's accelerating to the left. So if I try to apply Newton's laws to this box, I would say, well, there must be some force that's pushing this box to the left. But of course, there really is no force pushing this box to the left. This is not what is happening, okay? This is wrong here, okay? So, right, if I'm in a moving reference frame, if I'm in a reference frame that is accelerating, then a box that's sitting still will look like it's accelerating. It's going to look like it's accelerating in the opposite direction, okay? But that box isn't really accelerating, and there is no force that is being applied to that box that causes it to accelerate. So if I try to apply Newton's laws, right? So, for example, if I see this box, I apply Newton's laws, I say, well, okay, we've got this force due to gravity that's pointing down. I've got a normal force that's pointing up. And yet, from my reference frame, I have an acceleration that's non-zero. But the sum of my forces acting on the box is 0, right? So Newton's laws don't apply in an accelerating reference frame. We can immediately see why, right? If I'm in a reference frame that's accelerating, then this box that's at rest looks like it's accelerating too, but the net force acting on it is 0. So Newton's laws just completely break once we're in a non-inertial reference frame. So let me go ahead and consider this is a really common example. So if I consider, for example, a person who's sitting in a car seat. So let me try to draw this as best as I can. So we've got a car seat here. We've got the stick figure here who's in the car seat. Okay? So if you're in a car seat, if you're in a car that's accelerating, and you consider what's happening inside the reference frame of the accelerating car, okay? Well, inside the reference frame of the accelerating car, you're not moving, right? If you're inside the car, for example, imagine if you're inside a car and you look at the person who's next to you. That person is at rest with respect to your reference frame inside that accelerating car, okay? And what you might be tempted to do is you would say, well, yeah, that makes sense. If I'm in an accelerating car, right, when you push down on the gas pedal, when you push the accelerator in your car, right, you feel like there's this force that's pushing back on you. And you'd say, okay, well, I've got this force pushing back on me, and then to cancel that, there's this force that the chair exerts on me, this normal force, right? Because, of course, the chair is made out of some hard material. You can't pass through it, so the chair exerts a normal force against your back, and that cancels this force that you're feeling when you push on the accelerator pedal and you start accelerating the car. This is not right, okay? Again, this is wrong, okay? This is wrong because you're trying to apply Newton's laws to an accelerating reference frame. The reference frame inside an accelerating car is a non-inertial reference frame. Okay, in fact, there is no force that's pushing you back in your seat. And the way we can see this is consider now a person who's standing on the side of the road. So if your car were completely invisible, and the only thing this person could see who's standing on the side of the road is you sitting in your chair, they would see you sitting in your chair accelerating to the right. Right? So they would see you accelerating. And they would say, okay, well, if I apply Newton's laws to this person who's in this chair that's just accelerating to the right, they would say, well, okay, then that means there must be a net force that's pushing them in that direction. And in fact, that is what's happening, right? We've got this normal force that the chair exerts against your back, and that's what's causing you to accelerate forward. This is a correct free body diagram. This is the correct way to do things, okay? And the reason we can do this is because this is an inertial reference frame. If I'm standing on the side of the road, then I'm moving with a constant velocity, namely 0 meters per second, and if I apply Newton's laws, everything will work out okay. So, in fact, when you push on a gas pedal and you feel this force pushing you back in your seat, that force that you're feeling is actually the force that the chair is exerting against your back and is pushing you forward. There is no force that is actually pushing you back into the seat. Okay, it's just the force of the seat pushing against your back, causing you to accelerate. Okay, so let's look at a example. This example says a cup of coffee is sitting on a table in an airplane that is flying at a constant altitude. The coefficient of static friction between the coffee and the table is equal to 0.3. This should say S. This is the static friction. How fast can the plane accelerate without the coffee sliding on the table? Okay, so let me go ahead and write down our known and unknown values. So we were given the coefficient of static friction, that was 0.3. And what I'm asked to find is what is the maximum acceleration. I think that was all I was given. So let's go ahead and draw a free body diagram of this. So here's the table, and on the table I have this cup of coffee. So there are three forces acting on this. There's the force due to gravity, of course, and the normal force. And now there's one other force, and to really see what's going on, imagine that you were, again, the whole plane was invisible, and the only thing you saw was this cup of coffee sitting on a table. Okay? If the plane is accelerating, then you see the cup of coffee accelerating with the plane. So we can see, right, that there is this force, this frictional force, and it's this frictional force that's actually pulling the coffee along with the plane. It's the force that's causing this cup of coffee to accelerate with the plane. So even though from within the plane it looks as though the cup of coffee is at rest, the cup of coffee is actually accelerating. The cup of coffee looks like it's at rest inside the plane, but the plane is a non-inertial reference frame. The plane itself is accelerating. So you have to consider what this looks like in an inertial reference frame. If you were outside the plane at rest, you see the plane accelerating to the right, so the cup of coffee inside the plane is also accelerating to the right with it. Now the cup of coffee is going to start to slide if the force that's dragging it forward, this frictional force, is too small to cause the cup of coffee to accelerate at the same rate as the plane. So the maximum frictional force we know is equal to mu sub s times the normal force, and what we're trying to solve for is what that maximum acceleration is that the static frictional force can exert, or can cause. Okay, well, my normal force is really simple. This is a horizontal table, so the normal force cancels the gravitational force, so this is just mu sub s mg is equal to ma max. Canceling the m's, we see that the maximum acceleration is just equal to the static coefficient of friction times g. And finally, if I plug this into a calculator, see I've got a cheat sheet somewhere where I've calculated this. Oh, there it is. It's equal to 2.94 meters per second squared. So that's the maximum acceleration of the plane without the cup of coffee slipping. Oh, apparently I left this slide in. So let's go ahead and look at another example. So this example says we have two side-by-side boxes that are being pushed by a force P. Box 1 has a mass of 25 kilograms, and box 4 has a mass of 4 kilograms. When this applied force P is large enough, box 2 is going to stick to the side of box 1, and it's going to be held there against the force of gravity due to the frictional force between these two boxes. If the static frictional force between these two boxes is 0.71, how fast must this acceleration be, or how large must this force be, so that this box M2 stays stuck to box M1 and doesn't slide down? Okay, so this is this idea like you've seen in the cartoons where there's like this jet or something that starts accelerating real fast, and the cartoon character gets pushed to the back of the jet or whatever it is, they get stuck against the wall and they don't slide, they just get stuck there. That's what's happening here to this box. So this whole thing is accelerating to the right so fast that this box is just stuck there, okay? It's not going to slide down, even though gravity's pulling down, because there's this frictional force that's going to push up on this box. Okay, so how do we solve this? Let me go ahead, let me open up a white screen here. Let me write down my known and unknowns. So we have that there's this M1 that's 25 kilograms. M2 is 4 kilograms. I have the static coefficient of friction is equal to 0.71. And I'm asked to find this force P. And to find the force P, really what I'm going to look for is I'm going to find the acceleration. So if I find the acceleration that's necessary, then I can find the force that we have to exert using Newton's second law. Okay. So let me go ahead and draw a free body diagram of these two boxes. So here we've got box 1. And again, let me do a little dashed line here for box 2. So there's going to be, I guess, 4 forces being exerted on this box. There's this force due to gravity and the normal force. They're not really important. Then there's this force P, right, that we're pushing these boxes with. And then there's the force that box 2 exerts on box 1. Likewise, if I draw a free body diagram for box 2, again let me use a little dashed line for box 1 now. This has 3 forces acting on it. This has the force the box 1 exerts on box 2. It has a gravitational force, but for this box, the force that cancels the gravitational force is the static frictional force between these two boxes. Okay? So, looking at this picture over here on the right, this is a really, really neat example, and I like to do this example because the static frictional force, right, the maximum static frictional force is equal to mu sub s times the normal force. And we're so used to saying the normal force is equal to the force due to gravity, but remember, the normal force is the force that is perpendicular to the surface. Here's my surface. My surface is between these two boxes. The force that's perpendicular to that surface is this force right here, the force exerted by box 1 on box 2. This is my normal force. Okay, and again, look at this. My static frictional force is pointing up. Normally, we have normal force pointing up like it is here, okay? Here, the static frictional force points up. The static frictional force is pointing up, right? Because this is parallel to the surface. Frictional forces always point parallel to the surface. and it's opposing any other force that's being applied parallel to the surface. In this case, the force due to gravity is pointing parallel to the surface right here, the surface of contact between these two boxes. So applying Newton's second law, we can see my static frictional force has to be canceling the force due to gravity if the box is not accelerating down. So my static frictional force has to be equal to the force due to gravity. And the static frictional force is the force that box 1 exerts, the static frictional force is mu sub s, I'm getting ahead of myself, times the normal force. And this is mu sub s times the force that box 1 exerts on box 2. So looking at this now, I could solve for the force that box 1 exerts on box 2. And once I know the force that box 1 exerts on box 2, I can use Newton's second law to figure out the acceleration of this box. And once I know the acceleration of this box, I can then use Newton's second law again on this whole system to find the net force that we have to apply. So solving for F1 on F2, this is the force that box 1 exerts on box 2. This is m. I should put a 2 here. This is box 2. This is m sub 2 g divided by mu sub s. So this is the force that box 1 exerts on box 2. Now if I apply Newton's second law to this, right, the net force acting on box 2 is equal to m2 times a. Well, the net force acting on box 2 is just this force that box 1 exerts on box 2. So solving for my acceleration, I see that it's equal to F1 on 2 divided by m2. But this is equal to this thing right here, this m2 divided by g over mu sub s divided by m2. m2's cancel, and I get that this is equal to g divided by the static coefficient of friction. Okay? So my acceleration of these boxes is equal to g over mu sub s. Finally, if I want to solve for p, I apply Newton's second law to this entire thing. Okay? So again, when I have two boxes and they're being pushed with the same acceleration, I can treat them like a single object. It has the mass that's equal to the sum of these two things. So I can treat this like an m1 plus m2 object times my acceleration, g over mu sub s. So if I plug all this into a calculator, I've got 25 kilograms here, I've got 4 kilograms there, times 9.8 divided by 0.71. See, I've got a cheat sheet somewhere here. Here we go. This is going to be equal to 400 newtons. Oops. That's equal to 400 newtons. Oh, I just closed that screen. Oh well. So I think I'm going to end this video there, and in the next video I'm going to talk about another application of non-inertial reference frames, which is apparent weight. And that's the weight that you feel like you weigh if you're in a non-inertial reference frame.